Hi, I'm Stuart Harrington, your guide to the essentials of Algebra 1. Welcome to Module 5 of this series. Module 5 is going to be building off of Module 4, where we did a lot of work with slope-intercept form, and those types of topics. This is actually an application of the slope concept. Today, specifically, we're going to be looking at calculating the rate of change that might be related to certain real-life situations that occur very commonly in our world. So, without further conversation, let's dive right in and see what we have in store for today. First, we want to take a peek at the objective for today's learning. It's very short, a simple one-sentence statement. We are going to be calculating the rate of change based on information that's going to be presented in a table, information that's going to be presented in a graph, or information that's going to be presented to us in just an algebraic equation. It's that simple. We'll look at all three of those types of problems. Now, before we dive into that, let's take a look at some vocabulary just to make sure that we all have a good common understanding of the terminology that we're going to have. So you see the terminology here. First one is obviously the rate of change. What we're going to be doing is comparing two quantities together. How much quantity 1 changes relative to quantity 2. It's going to be a ratio. It's going to be a fraction. The good news is that the rate of change is something you already know how to calculate. You just don't realize it yet. The rate of change is identical to the slope. If you are good at finding slope, then you're going to be good at finding the rate of change. If you're not really comfortable with finding slope yet, today you will get additional practice in doing that. So this benefits everybody. We're either going to get better at what we do, or we're going to have the opportunity to kind of chill out and relax a little bit because we already know how to do it. So rate of change is a comparison of two numbers, and it is the slope. The other terminology that we've got there, it shouldn't be any surprise what a table is. It's going to be a chart that's got some numbers on it. We're going to work with those. We're going to look at graphs. You know that those are simply pictures of lines that give us a lot of data if we know how and what to look for. And then finally, a linear function. We have worked with those before. We're going to be taking a look at those and working with them in our work today. Now, the last thing I've got on the list is this long word called algebraically. When we talk about solving something algebraically or figuring something out algebraically, that means we are not looking at a picture, right? We are literally taking some equations and using our addition property, subtraction property, multiplication property, division property, and manipulating an equation. Like when we solve two-step equations, when we solve multiple-step equations, when we do things like moving the x's all to the left and all the numbers to the right, or all the y's to the left and all the x's to the right, that sort of thing. When we manipulate, that means we are working on the equation algebraically. And we'll use that term a few times. You may have heard it before. Just want to make sure you understand what we're talking about there. So that's our vocabulary. So let's dive right in and let's take a look at how we're going to solve some problems. I mentioned a few minutes ago that slope and rate of change were the same thing. So before we get started on working these problems, let's take a quick review of the formula that we use to solve slope. It's this one right here. Remember, you're going to have 2 points of data. You're going to have an x and a y value in each point, first point and second point. And so the formula for slope is talking about how does the y value change, delta y, we introduced that term last module, and delta x, y sub 2 minus y sub 1. We read that as the y value of the second point minus the y value of the first point. And that's going to be divided by the x value of the second point minus the x value of the first point. That is going to result in a fraction most of the time. It can be positive or negative. If it doesn't result in a fraction, it'll be simply a whole number, which means we put it over 1 to get our fraction. So, change in y divided by the change of x. And we're going to use that to solve some problems. So let's take a look at this chart right here. We've got some data, and this data is relative to the height of a candle as it burns over time. Now, if you enjoy burning candles in your home because it provides a pleasant environment, then you will understand that the longer you burn a candle, the shorter it's going to get. So we've got this candle here that at time equal to 0, it's 10 inches tall. All right, so this is one of those large candles that you might buy in a specialty shop or something like that. After 2 hours of burning, it's down to 7 inches, and after 5 hours, it's down to 2.5 inches. So what is the rate of change of the height? Well, we want to make sure that you understand that in a table, x's are generally going to be here on the left, and the y values are here on the right. These actually constitute points: 0, 10, 2, 7, and 5, 2.5. So to find the rate of change, we already know that means slope, we're going to identify one of these as 0.2 and one of them as 0.1 and work the formula. So to do that, let's go ahead and we're just going to say our first point here is going to be point number 1, and we'll let this one be point number 2. So let's just plug and play into the formula. The y value of the second point, that's going to be 7. And then the y value of the first point is 10. So 7 minus 10, and we're going to divide that by x of the second point minus x of the first point. That's going to be 2 minus 0. So 2 minus 0. And we do the math on that. 7 minus 10 is going to be negative 3. 2 minus 0 is going to be 2. Negative 3 over 2 is the fraction. It does not reduce. Consequently, what we have is our rate of change of the candle, inches relative to hours. It decreases 3 inches every 2 hours. That's the rate of change. And so you would simply say the rate of change, aka ROC, is going to be equal to negative 3 over 2. That's all you got to do. That's simple. Let's look at another one. In this particular table, we are computing or reporting data relative to the value of a baseball card. When you first purchase the baseball card, it's going to be time of 0. Its value is going to be $10. After 2 years, that value is going to be $20. And after 10 years of laying in some folder or some display case somewhere, it's going to be worth $60. What we want to determine is, what is the rate of change? Now, is that value going up or is it going down? Value's going up. What kind of a slope, in terms of the sign of the slope, do you expect that to be? Positive or negative? I would expect it to be positive as well, because the value is going up. A moment ago with our candle, that value was decreasing. The height of that candle was going down, so we would have anticipated that the rate of change would be negative, and that's what it turned out to be. This one, the value is going up. We anticipate the rate of change to be positive. So let's do the calculation again. Now, when you are working problems with tables, it doesn't matter which point you choose as point number 1 or point number 2. You're given 3 alternatives. We've got 3 points here. We don't have to be given 3. As long as we're given 2, we're golden. Okay? But we're going to have 3 points here. So just for fun, we're going to take the last row here, and we're going to call this our point number 1. And we'll take the second row, and we'll call this one our point number 2. And then we'll go and plug in the formula. Now, if you want to work it out using another choice, you can, or you can work it along here with us. But let's plug it in. What's the y value of our second point minus the y value of the first point? 20 minus 60. So 20 minus 60 is going to be the first one. And then the x value of the second point minus the x value of the first point, 2 minus 10. That's going to give me negative 40 over negative 8 when I do the math. That is a fraction that can be reduced. Negative 40 over negative 8. First of all, negative divided by a negative, that's a positive. It's kind of what we expected a minute ago, that we would have a positive slope. And then 40 over 8, that divides out evenly, actually, to 5. And so what is the rate of change of the value relative to time? The rate of change is 5. What does that mean? It increases $5 per year. 5 over 1. All right? So we would simply say the rate of change is going to be equal to 5. That is a couple of problems involving tables. Let's transition to graphs. I would anticipate graphs will be a little bit easier to do, simply because we have grids that we can look at and simply count spaces. And this first example is proof of that. Take a look at this one. We don't really know what our units are or what this graph represents. It's just simply a linear function that's representing some rate of change, and we need to analyze it and determine what is the rate of change. Now, I'm leaving the formula for the slope on the screen, but I don't think we're going to need it for this one because we can simply look at the graph. And by looking at the graph, I am noticing things like, well, I need to know how much does the y value change compared to the x. So we represented that in last module with delta y, delta x. Remember that Greek letter delta represented change. So the change of the y value divided by the change of the x. That's exactly what we say up here in this formula. It's just written kind of in a symbolic form. So let's look at the change of the y value. Let's compare from point A to point D. What happens? It goes up 9. The y value goes from way down here at negative 4 to all the way up here at positive 5. And so that is an up 9 change, which means that is a positive number, positive 9. Now what about the x values? The x value here is at negative 3. This x value over here is positive 3. So that means we went over 6. 1, 2, 3, 4, 5, 6. Count it, subtract it, however you want to calculate that. So the change of x is going to be 6. Now that is a fraction that does reduce to 3 over 2 because 9 and 6 both divide by 3. Consequently, the rate of change for this guy is going to be 3 over 2. Makes sense? Now, what if you didn't pick points A and D? What if you picked points A and C? Points A and C. How is that going to look? Well, let's take a peek at that. We're going to go from point A, which is right here on the y-axis, up to here, which is point C on the y-axis, and that's going up 1, 2, 3, 4, 5, 6. And what about the x value? The x value is going from here on point A to over here on point C. What does that change? 1, 2, 3, 4. So we've got 6 over 4 as being our delta y over delta x. And 6 over 4, both of those numbers divide by 2, is 3 over 2. You get the same answer. Okay? It doesn't matter which 2 points you select. You just pick 2 points, calculate the delta y, the change of y, calculate the delta x, the change of x, and write the fraction, and you're done. Let's look at another graph right quick. Now on this particular graph, we are looking at a picture of the value of a computer over time. Look closely at your x-axis and your y-axis. The x-axis is labeled months. The y-axis is labeled the value or the dollar amount that that computer is worth. You have to pay attention to the scale that the grid is showing for you. The graph we had a minute ago was just one line for every one number. 1, 2, 3, etc. This one's a little bit different. Look at what you've got going here. Every grid line is 2 months, 2, 4, 6, 8, etc. All right. Going up the y-axis, the value in dollars. What's every grid line worth? It's actually worth 100, because on the second grid line we call that 200, and the next one that's labeled is 400. So what's not labeled for us is this one right here, which is 300, 100. So I'm not going to label all of those, but that's something you need to watch as you go through and work problems on graphs, is how is the graph labeled and scaled? That's the important word there. How is it scaled? And so value of the computer on the y-axis, number of months on the x-axis. Again, we want to find the rate of change. Look at the line. Is the line going down or is it going up? I'm going to look at the right-hand side of that guy, and that line is going down. What sort of rate of change are you going to expect, positive or negative? Going to expect a negative. Let's go and see if we can calculate it. Now, we've got 2 points that are given to us. We'll label those. This will be our point number 1, and this will be our point number 2. And we want to calculate the change of y over the change of x. Now let's do that first just by looking at the graph. What is the change of the y value? It goes from up here to here. How far is that? Don't say 2 spaces, because that's not the scale. Each space is worth how much? It's worth $100. So going down 2 grid lines is going down $200. And so the delta y is going to be negative 200. Now what about the x value? The x value of 0.1 is right here. That's at 2. The other one is right here, and that's at 12. So it's gone from 2 to 12. If I wanted to count that, I would count 1, 2, 3, 4, 5 grid lines. But it's not 5 because each grid line is worth 2. Keep your eye on the scale. It's actually going up 2, 4, 6, 8, 10 units. So delta x is going to be 10. Negative 200 over 10, that's going to be a negative answer. And 200 divided by 10, well, that's just 20. So our rate of change is negative 20. Now, a couple of observations on that. First of all, it indeed was negative. We expected that because the line's going down. The second thing is that there's no second number. It's just negative 20. So what is the rate of change? It's negative 20 over 1. But for mathematical purposes, you can simply say that your ROC is going to be equal to negative 20. Okay. The trick and the thing to remember from this problem, pay attention to the scale of the graph. It makes all the difference. Quickly, let's rework this problem using the formula. Suppose I didn't want to count points, I just wanted to use the y2 minus y1 information. All right. My point number 1, I need to identify the coordinates of that. So the coordinates of point 1 are going to be 2 and then 900. And the coordinates of point 2 are going to be 12, 700. Now I just plug those into my slope formula. Y of the second point, 700, minus y of the first point, 900, divided by x of the second point minus x of the first point. That's going to be 200 negative, because 700 minus 900 is negative 200. And we're still going to get 10 right here. And that's still going to be negative 20 right there. So you can see there and there, we got the same result. You can count spaces if you're careful with the scaling, or you can use the formula. Again, you got to be careful with the scaling. Now, that's a couple of graphs that we've looked at. The third type of environment that we were looking at today in our objective, we need to pay attention to just algebraic equations. How are we going to do that? Well, let's take a look at some of those right now. Now, before we begin, let me remind you of one of the forms of linear equations that we often work with, and that is slope-intercept form. It looks like this. Y is equal to m times x plus b. M represents the slope, b represents the y-intercept. X and y represent points on the graph. That's all information that you know already. Why am I reminding you of this? Because when we get equations given to us, we need to be able to look at them in terms of slope-intercept form. For example, if I give you an equation that says y is equal to 2/3 x plus 7, what is the slope of that, friend? It's 2/3. So the slope of that guy is going to be 2/3. And so if that equation represents a real-world scenario or a rate of change problem, then our rate of change is going to be equal to 2/3. It's that simple. Okay. What if we have y is equal to 5x minus 6? What if that's our equation? Well, our slope is no longer 2/3. Our rate of change will not be 2/3. What will it be? It's now going to be 5, because that's the number in front of the x. And our rate of change is going to be 5. So the rate of change is going to be 5 to 1. It's very simple. What if it's this? Make a quick change. Instead of 5x, let's suppose it's negative 4/5 x minus 6. Our slope is now no longer going to be 5, it's now negative 4/5. And the rate of change? Negative 4/5. So negative 4 to 5 is going to be the rate of change. That's straightforward. Now the problem is we're not always going to be given equations that are in slope-intercept form, simply because they're pretty easy. We are going to get equations given to us in all kinds of shape or form, and we have to work on them algebraically. There's that word again. We have to work on them algebraically to convert whatever we're given into slope-intercept form. What am I talking about? What if I have this? 4x minus 2y equal to 10. Now, this is a linear equation. How do I know that? It's because it has an x and a y in it. What is the rate of change for this linear equation? I have to convert it to slope-intercept form using my algebraic properties. Now, I have a 4x minus 2y equal to 10. I need to make this statement into this format, which means I have to get the y all by itself. 4x, got to go. Negative 2, got to go. How am I going to get rid of the 4x? Well, we're going to get rid of the 4x by subtracting it on both sides. Minus 4x, minus 4x. And then we're going to change that. That's going to cancel out right there. So negative 2y is going to be equal to negative 4x plus 10. Now, are we in slope-intercept form yet? Not quite, because we got to get rid of the negative 2. So I'm going to have to divide everything by negative 2. That will cancel out on the left-hand side and just leave me with the y. But what about the right-hand side? We've got to divide everything over there by negative 2. So I'm going to be looking at negative 4 divided by negative 2. That's going to be a positive 2x. And then I need to look at 10 divided by negative 2. It's negative 5. Now my equation is in the slope-intercept form. Now and only now am I allowed to look at it for the slope. The slope is going to be 2, and that means the rate of change is going to be 2 as well. All right? 2 to 1. Rate of change. One thing is changing at 2 times every time the other unit is changing once. Let's do another one. The next problem we're going to do is 3x plus 4y equals 8. Again, this one is not in slope-intercept form. We can't simply look at this 3 and say, oh, that's going to be the slope. No, that only works when it's y by itself equal to m times x plus b. That's the only time we can look at the number in front of x, the coefficient of x, and say, oh, that's the slope. So I've got to work on this. I've got to get the y all by itself. This guy right here has to be all by itself. We've got to work on it until we have y by itself equal to something. Okay? So we're going to do that. We're going to have to get rid of the 3x. So we're going to go minus 3x, and we've got to do that on both sides. Doing that, those guys go away. We have a 4y equal to negative 3x plus 8. How do I know it's plus 8? It's because it's a positive 8. Now you may have noticed, how do I know to put the 3x first? Because I'm just trying to model the slope-intercept form. You could write 8 minus 3x if you wanted to, but that's not in slope order, this slope-intercept order. So that's why I choose to go ahead and put the negative 3x plus 8. Just makes things easier for me down the line. Now I need to get the y by itself. So we've got a 4 hanging there with it. So we're going to have to divide by 4 and everything by 4 over here. On the left, the 4's cancel out. And there we are. We've got our y all by itself. That was what we were shooting for. Now over here, this 4, remember, has to divide here. And it has to divide here. Negative 3 divided by 4, that's just a fraction. Negative 3/4. It doesn't reduce, it doesn't divide out evenly, it's just negative 3/4. And then you got the x with it, and then you've got 8 over 4, 8 divided by 4, which is 2. So there's my form. It's now in slope-intercept form. It looks exactly like the model that we've been targeting. Okay, so what is the slope of this line? Slope of this line is negative 3 over 4. What's the rate of change? It's negative 3 to 4. Negative 3 to 4. One quantity is going down 3 every time the other quantity is going up 4. Okay? So this is a negative slope. This is a negative rate of change. It's a line that's going down. So something is decreasing as something else increases. That concludes our content work for this particular session. We have discussed how to calculate the rate of change when we're looking at data presented in a table format, in a graph, or in just a simple algebraic equation. We've talked about the ramifications of that in terms of positive versus negative. We've talked about how it doesn't matter which point you choose to be point number 1 or point number 2. You can count spaces on the graph. You can use the slope formula, or you can make a conversion to slope-intercept form if you are working with equations. Okay, lots of things. Let's go practice those. We'll see you next in video number 2. Bye-bye.